Morning, everybody. So, welcome to Physical Pharmaceutics class, where we have started Complexation chapter in the last class. That is, we started off with the new chapter that is Complexation and protein binding. In the last class, that is in Monday's class, we studied all about the introduction to complexation. We studied about its applications, as well as we studied about the basic types and what are the properties where it finds the changes or it finds alterations in some of the physical properties on complexation of drugs, as well as we studied about the basic terminologies such as ligands, coordination number, what is substrate, what is ligand, and Chile, sequestering agent, etc. So after all that, we started off with classification. And I told you, you can refer both the textbooks for classification. Here in CVS, they have given a very uh, concise kind of classification, whereas in case of Manabalan, he has given very elaborated classification. It will be one and the same. That is much more in detail in Manabalan. In CVS, it is concise. That's it. So here, if we have to classify the complexes, am I audible? Am I clear? Okay, thank you. Thank you, Salman. So here, I told you, speaking about the first type of complexes, that is the metal complexes. In case of metal complexes, we have inorganic types, chelates, olefins, and aromatic types. So in today's class, first we'll try to study or concentrate on what are these types, what are these metal complexes, metal ion complexes. Okay. So coming to the first type, that is inorganic types. Now I had told you in the last class or in the first class that metal ion coordination complexes means it consists of or it has the interaction of metal ion, which is a substrate, and with the other interactant, where the other interactant can be organic molecule or it may be an inorganic molecule. And the bond which is formed between the substrate and the ligand here in these metal ion coordination complexes is the coordination bonds. Are you able to correlate? Please correlate. That is, try to recall whatever we studied under metal ion coordination complexes from Manabalan textbook. Metal ion coordination complexes. It has a metal as a substrate and it has a ligand which may be organic or inorganic or some ion molecule. And then in these two, that is the interaction between the substrate and the ligand is mainly because of the coordination bonds which will be formed. So all these mechanisms leads to the formation of metal ion coordination complexes, and in that the first one what we are having is inorganic type. Now firstly, in simple terms, if I have to tell you about inorganic type, that is, if you refer if you go to this Manabalan textbook, here very briefly they have given about metal ion coordination complexes, in that the first one, that is inorganic type. But this won't be sufficient. This won't be sufficient for your exam. Here they include simple inorganic complexes. The middle coordination complexes, they include very simple inorganic complexes and described by Werner. It has been described by Werner. Okay, Werner postulates. And here, for example, they have given the example, that is when ammonia is treated with cobalt chloride. When ammonia, that is NH3, it is treated with cobalt chloride. Okay, here it forms a complex which is called as hexamine cobalt 3 chloride. Hexamine, here you can see 6 amine, hexamine cobalt 3, cobalt 3 chloride. This is the complex which is formed on interaction of ammonia. Ammonia is the ligand. Substrate is this cobalt chloride. And the interaction between them leading to the formation of coordination bonds results in a complex where we call this complex as hexamine cobalt 3 chloride. In this, each ammonia molecule donates one pair of electrons, and it forms a coordinate bond with the cobalt ion. Here, cobalt is the metal ion, that is the substrate. So, this is the example for inorganic type. Some other examples are, here you can see silver acting as the metal ion, Ag, and ammonia is the ligand. So silver chloride with ammonia, ammonia interacting with silver chloride leads to the formation of a complex. And the other example is chromium with water molecules over here. So these are some of the examples. Now the detailed mechanism, here they have given in CVS textbook. Here they have given the detailed explanation. Inorganic types or inorganic complexes. Here, Werner, he has enumerated a number of rules. Werner is the chemist who came across so many rules and postulated certain theories by which some of the deviations from the classical theories of valency can be rationalized, or he came up with his own postulates. And according to him, the first point is there are two types of valencies. He says that just a second, one of your classmates cannot connect the class. Okay. So here, the first point what he tells is, he tells that there are two types of valencies. He tells there are ionic and coordinate, or there are primary and the secondary. He tells that there are two types of valencies, that is primary valencies and secondary valencies. Okay, that is his first point. Next, what he says is that the same type of anion or radical or a molecule may be held by individually or both types of valences. Now, when there are valences, it is held up or it is occupied some kind of anion or a radical or a molecule, and this may be held by individually, or individually means it means only primary valency can be holding this molecule, or both the type of valences may be holding these molecules. Both the type in the sense both the primary valency as well as secondary valency, both are occupying or both are taking up these molecules. Or it may so happen that only one type of valency is taking up these molecules. It may be only the primary or the secondary or both. So first what he told, there are two types of valences, primary and secondary. Now the molecules can be taken up by either primary or secondary or both. That is his second postulate. Hope you are getting my point. Now, next, he came up with the third statement or the third postulate. But actually this third postulate we already studied in the last class. He tells that, because already as per Malala textbook I had taught you all this. He tells that for each central atom or ion, that is for example, for a central metal ion, there will be some fixed number of non-ionic valencies. Fixed number of valencies. That is what I told you, that it is called as the coordination number. Every molecule or every metal ion will be having a fixed bonds found between the metal ion and the ligand, and that number is nothing but the coordination number. And here the coordinated atoms or groups occupy usually the first sphere or the coordination sphere. So usually there will be two spheres always, and the coordinated atoms always first occupy the first sphere, where first sphere we also call it as the coordination sphere. It is the complex formed by the coordination bonds, and the other atoms are said to be in the second or maybe the ionization sphere. Here the second sphere, the second set of interaction, we call it as the second sphere or ionization sphere. Okay. Next, neutral molecules as well as ions may satisfy the non-ionic valencies. Now, neutral molecules as well as ions, it will satisfy the non-ionic valencies. Means you can see here, it has the tendency to attach to the central metal ion. The neutral molecules, or it may be some ions, ammonia ions or whatever ions, they first satisfy these non-ionic valencies, leading to the formation of coordination complexes. And the next point is the non-ionic valencies are directed toward definite positions, that is definite space or maybe the valency or stereoisomerization. That is, they are very much specific towards their positioning. That is, at the non-ionic valencies, the interaction by the ions with the valency of this metal ion, it will be having a definite position. Now, this I'll explain with the help of an example. Here in the diagram, you can see here there is ammonia, and then there is cobalt fluoride, and here we can see the coordination sphere and the ionization sphere. The first sphere, here whatever is happening at the center, that is called as the coordination sphere, and the next sphere or the second sphere is this ionization sphere, which consists of the fluorine ions. Okay. Now let us see to this. In solution, this compound, which compound is that? That is the compound consisting of cobalt fluoride with ammonia, ammonia treated with cobalt fluoride. Here it forms or it ionizes. The cobalt fluoride, it ionizes to CuCl NH3 5. But actually it should be 6. As per Malala textbook, it should be 6. And also it leads to, this is one kind of ion, and the other ion is this fluoride ion. This is the first ion which is formed during ionization of this compound, and the second set of ions generated will be the chloride ion. Now, the chloride ion is the coordinated sphere, and it cannot be precipitated by silver nitrate. No, student, actually this sentence they have given wrong in this textbook. Actually, this is all related to the next set of example. Okay, so forget about the second point. Now here, groups such as Cl and NH3 in the coordinated sphere. Coordinated sphere means in the first sphere, they are called as the ligands. That is, they always donate a pair of electrons to the substrate of the central atom. So here you can see that the chlorine ion and the ammonia ions, these are the ligands. They are showing it over here. The Cl ion and NH3 ion which are present in the coordination sphere, these are the ligands. It means these have the tendency to donate the pair of electrons to the substrate. Substrate means here it is a central atom, that is this, cobalt is the substrate. So if Cl and NH3 are the ligands, cobalt is the substrate. Okay. Now, the type of bonding between the metal and ligand may be electrostatic or covalent. Okay. So, what kind of bond will be formed here? It may be the electrostatic kind of interaction or the covalent bonding. Now, here already we have studied the same point he has mentioned here. That is, the coordination number of central atom is the maximum number of atoms or groups that can combine with the central atom in the coordinated sphere. I had told you every central atom will have some fixed number of vacancies, or it will have fixed number of bonds that can be bonded with the ligand. That is, the maximum number, coordination number of the central atom or the metal ion is the maximum number of groups. It can take only that particular definite maximum number of groups from the ligand. It can combine with the central atom in the coordinated sphere. Coordinated sphere in the sense the central sphere or the primary sphere or the first sphere. And here coordination number is usually an even number. That is, we studied for cobalt, the coordination number is 6. That is, cobalt can take up maximum of 6 sharing, 6 bonds with that of the ligand. Yeah, here you can see that it has bonded with 5 ammonia ions and 1 chlorine ion. So 5 plus 1 forms 6. So the coordination number of this cobalt is 6, where it has formed bonds with 6 of the ligand groups. Getting my point? So that is what is mentioned in the point 5. Now, like this, I explained that, or this is the mechanism of complex formation, where there will be cobalt chloride, ammonia. On ionization, it forms ions as shown in the first point. And here the Cn and NH3 in the coordination sphere, these are the ligands which have the tendency to donate the pair of electron to the central atom. Central atom, that is cobalt, which is also acting as the substrate. And every central atom or the metal ion, it has a coordination number. That is, it can take up only till that maximum number of atoms or groups, and that number we called as the coordination number. And for cobalt, the coordination number is 6. That's the reason here it shows that it has taken up 5 ammonia ions and 1 chlorine ion, leading to the formation of complex. Now the same concept, if I have to explain in terms of hybridization, you would have studied about hybridization. Yes? Yeah, in your chemistry classes, you would have studied about hybridization concept. You would have studied about the orbitals and all that. D orbital, S orbital, P orbital. Now here, the concept of hybridization will be used over here to understand the coordinated compounds or metal ion coordination complexes. Here, for example, now ligands, they donate a pair of electrons in forming the complex. Yes, yes, that is what we study. For example, is water molecule or ammonia ion or NC or chlorine ion, etc. Now this electron pair is accepted by the metal ion, that is nothing but the substrate. Yes. So now in metals, all the orbitals such as s orbital, p orbital and d orbital are to be considered. So we have to check. So here, as I already told you, the coordination number of cobalt is 6. Here the trivalent cobalt ion, it has the following configuration, that is electronic configuration. It has 3D, where one of it is totally saturated and the rest 4 are unsaturated. It has 1 4s and 3 4p. That is cobalt. It makes use of their 3D, 4s and 4p orbitals in forming the hybrids. But this type is different from the classical concept of hybridization. Here, this is totally different from the regular example or the classical example of hybridization what you study in the chemistry. Now here, in classical theory, what happens usually the electron pair is promoted to unfilled orbitals, isn't it? The electron pair, it will be promoted or it will be given up to the unfilled orbitals. And here what happens is these half-filled orbitals, unsaturated orbitals, further involved in the chemical bonding. Whereas now you can see in the complexation, I told you that this was totally filled or it was saturated, whereas 1, 2, 3, 4 was unsaturated. But what they did is, what the 3D orbitals did is, it gave up its pair of electrons to its unfilled orbital. So now 2 gets filled and we are left with 2 unfilled orbitals in 3D. That is, in complexation, the electron in a half-filled orbitals. Electron in half-filled orbitals means, here also it was initially how? This orbital was shown like this. Okay, consider it as a dot. Yeah. Now what they did? The electrons in the half-filled orbital shift to the other orbitals so that it can fill them up. Fill them as electron pair. So what they did? From here the electron pair moved to this one, so now it got totally filled up. From here it moved to this one, so even this one got filled up. So there are no more unfilled parts. There are no more unfilled orbitals. Now this creates completely vacant orbitals in the metal electronic configuration, and the electronic configuration of the metal ion leading to filled 3D level is, that is, upon sharing or upon giving up its pair of electrons, now the unfilled orbitals what we are left over is D2, that is 2 more orbitals in D, 1 4s and then 3 4p. That's the reason it is D2, 1 D2, 1 s orbital and 3 p orbital. So what we are left with, d square s p cube or d2 s p3. These are the unfilled or completely vacant orbitals. These are the completely vacant orbitals. Now, the ligands will donate. So, this is all about the substrate what I am speaking of. So, what is the work of the ligand? Ligand has a tendency to give away its pair of electrons to the substrate. So, the ligand, it will donate its pair of electrons to these vacant orbitals of the metal ion. So we are totally left with the 2d orbitals, 1s orbital and 3p orbital. So ligand will give away its pair of electrons to these vacant orbitals of the metal ion, resulting in the formation of complexes. Thus, the D2sp3, or we also call it as a octahedral structure in the complex using this technique. Here Werner has proved that the cobalt complexes are octahedral. Here I told you cobalt is having 6 coordination number, 1, 2, 3, See here, 2 plus 1, 3 plus 3, 6. So, like this, Warner proved that the cobalt complexes are octahedral structures, and the structure is shown with the ligand. Here, in the next diagram, you can see the structure with the ligand. Here you can see that there is the central metal ion cobalt, which is having coordination number 6. It means it can form bond with 6 different, that is 6 atoms or molecules. That is 6 ligand molecules or ions or atoms. So it is a octahedral structure. Is this clear now? In brief, what we understood is that cobalt is having coordination number 6. That is, 6 of its orbitals are unfilled or 6 of its orbitals are vacant, where those 6 vacant orbitals can easily take up the pair of electrons from the ligand. And here the ligand is the chlorine ions as well as the ammonia ions. So six ligands can give away its pair of electrons to fill up the vacant orbitals of the metal ion, leading to the formation of complexes. That is hexamine cobalt-3 chloride complex. Hexamine cobalt-3 chloride complex can be formed. So for 5 marks, if they ask you about, usually they'll ask you to explain metal complexes. So in that, the first one you're going to explain this, but explain in brief. Now moving on to the next type of metal ion coordination complexes, that is chelates. Already in the first class I briefed you about the chelates. Now a substance which is containing 2 or more donor groups, that is a chelating agent. It may combine with a metal to form a chelate. Chelate means it is a combination of metal and ligand, or a chelating agent which has the tendency, that is, it has the tendency to have 2 or more donor groups. That is, if a metal ion binds with a multidentate ligand in the sense, the ligand which is having 2 or more binding sites, it forms a cyclic complex, and that cyclic complex we call it as the chelate. The most common example is ethylene diamide. Ethylene diamide, it forms a chelate with copper. Here in the Manavaran textbook, here in the Manavaran textbook, you can find this chelates, and example is ethylene diamide. It forms a cyclic complex with copper too. That is, copper ion binding with ethylene diamide. So it results in the formation of ethylene diamide complex with copper too. Okay. And if I have to check with CVS, yeah, the same thing they have given here. Chelates, these are the group of metal ion complexes in which substance, that is the ligand, it gives away or it provides or it consists of 2 or more donor groups to combine with a metal ion. And usually what happens in inorganic metal complexes, if I have metal and an inorganic ligand, the ligand will provide only one side for binding with the metal. Whereas in chelate, what happens? The ligand will have 2 or more binding sites. 2 or more binding sites with that of the metal to form complexes. And depending upon the donor groups, These ligands, they are called as like unidentate. Unidentate means it has only one binding site. Bidentate means it has two groups for donating. Tridentate means three groups. Polydentate means more number of groups. Like that, we are having ethylene diamine tetraestic acid, EDTA. EDTA stands for ethylene diamine. Ethylene diamine. Diamine means two amine molecules. Tetraacetic. Tetra means four acetic acid molecules. So ethylene diamine tetraacetic acid is nothing but this EDTA, which has 6 points of attachment to the metal ion. That is, there are six donating groups in this EDTA. It has six donor groups where these six donor groups will attach with the metal ion. That is what they had shown. This is metal ion. 1, 2, 3, 4, 5, 6. Six donor groups are present in this EDTA2, and that's the reason EDTA we call it as hexadentate. EDTA is the ligand which has six donor groups or six binding sites, and this is called as a hexadentate. Now, in the diagram in page number 325, you can find the structure of EDTA. Ethylene, ethylene, diamine, tetraacetic acid. Ethylene means CH2, CH2, two groups. Okay, that is ethyl. Ethylene diamine means two amine groups, two amine molecules or ions, amine indicated by NHR, the rest of the things. Two amine, diamine. Tetraacetic, tetra means I told you four. Four acetic acid groups. Here you can see 1, 2, and 3, and 4. Tetraacetic acid. Okay, so that is the structure of ethylene diamine tetraacetic acid, that is EDTA. Now, this since this EDTA provides more points for binding, diverse type of bonds such as ionic bond or primary covalent or coordinated bonds are involved. So there may be different types of bonds which are formed in this EDTA complex. Now, these bonds can be seen in calcium EDTA chelate. Here you can see it in terms of calcium EDTA chelate. Or in general, if I have to show you the example of EDTA complex, so there is a central metal ion, okay, surrounded by this EDTA, leading to the formation of EDTA complex with the metal ion. And here you can see there are six bonds surrounding this metal ion. That's the reason here it is EDTA. We tell that it is hexadentate ligand. Now the dashed line, here whatever dashed line we have, that indicates bonds from the ion to the coordinated groups of the ligand. Okay. And EDTA provides six sites, that is hexadentate for complexation. And here the coordination number of this metal is 6, as we had seen in case of cobalt. Okay. So this is all about the example for chelates that you can see. And also in the very first class, students, it's getting late. Just a second. Let me take the attendance. Once I take the attendance, I'll continue with the class. Okay, I'm getting late, so we'll join back the class. Okay, I'll end the class now and then please join back.